Okay, so in the last video, we had a quick review of the Euclidean vector space, but you might be wondering, how does that relate to frequencies or Fourier series or anything like that? So it turns out that Fourier series pretty much are the same thing as that projection trick that we used with the inner products, except it acts on a more general vector space of functions on an interval. So in this video and in the next few videos, I'm going to be bridging some of the relations between the Euclidean vector space and more abstract vector spaces. So in this first one, I'll give an introduction into what a vector space actually is. So the way mathematicians have defined a vector space is you have a field of scalars, which you can just think of the real numbers because that's all we'll be using for now. And essentially just some set of numbers that you can scale by. And you have a set of things which are called vectors. And these are just your arrows in Euclidean space, but later we'll see more examples. And so essentially what you can do is you can add two vectors together and then you get another vector. Or you can scale a vector by your field of scalars and then you get another vector. And so these are the properties. If you want, you can pause it and read through them. But I'm going to explain them geometrically because it's not very complicated in this way. So one of them is that vector addition is commutative. So what that means is v plus w, which is this vector, gives you the same thing as w plus v, which is the same diagonal vector. For Euclidean spaces, this is often called a parallelogram rule because it makes a parallelogram. Another one is that there is a zero vector, which is just not going anywhere. And it says that if you add v to 0, then you get v. Or if you add 0 to v, then you get v again. And every vector v has a opposite vector negative v, so that when you add v plus negative v, it's pretty much go there and come back, and you end up back at 0. And then another property is that if you have three vectors u, v, and w, then you can do u plus v first, and then add that to w, which will give you this long vector. Or you can do v plus w first, which will give you this, and then u plus that gives you the third long vector. So all that's saying is that you add up three vectors, and then you get this long one. So those are some of the properties that you have for addition. You also have some properties that you have from scaling by numbers. So you have your vector v, and you can scale it up by some factor a. And so that'll give you this longer vector. It can also be shorter, but I just made it longer. And then you scale a v up again by another scalar v. So then you end up with a b v. And so what the scaling property says is essentially this is the same thing as just multiplying by ab directly and getting the longer vector. You can also, the vector scalar multiplication is distributive on the left, which means that you can multiply v by a scalar a and you get this vector. And then you can multiply it by v and then get this vector. Add those both together and you just get a plus b times v. Or it's also distributive on the right, which means that you add two vectors together and you get a third vector, u plus v. And you can just scale the entire picture up. And then you get au plus av, and you get a times u plus v. So these are fairly simple to understand, but mathematicians prefer this. And the reason is that a mathematical definition really has to be in a golden spot between being general enough so that you can apply it elsewhere and being specific enough that you can actually create a theory out of it. So if you say a vector space is a set with a thing, that's not very specific. You can't really do much with it. But you can find it pretty much everywhere. You know, everything is a thing. However, if you say like a vector space, there's just a Euclidean vector space. You can't really generalize that to the Fourier series or other interesting vector spaces. So that's a bit too restrictive. So this definition of the vector space gives just enough information where you can find it almost anywhere. And it gives so it gives enough information that you can find almost anywhere and that you can come up with something really interesting out of it. And usually you look at vector spaces from the point of view of linear algebra, but in these videos I'm going to instead be looking at it with inner products and the Fourier series. So after we introduce some vector space terminology in this video, I'll be going over the more generalized inner product and metric spaces in later videos, and then we'll put those all together into Fourier series. So now let's introduce an example of a vector space that's not going to be the Euclidean vector space. And that is going to be the vector space or the set of all quadratic polynomials with real coefficients. So that's ax squared plus bx plus c, where a, b, and c are real numbers. So your vectors in this case are going to be polynomials. So what do you need for a vector space? You need vector addition, and then you need scaling by your field of scalars, which is the real numbers. So here you have one vector a1 x squared plus b1 x plus c1, and then you have another vector a2 x squared plus b2 x plus c2. And if you add them together, it's just component-wise addition. You add together the x squared coefficients plus the x coefficients plus the c coefficients multiplied by x squared, x, and 1. And if you multiply your polynomial, or in this, which is your vector, by some real scalar, which is u, so this is any real number, then you just scale up each of the coefficients, and that'll give you a different vector in your vector space. So the way to interpret this is this polynomial represents a vector like u in your vector space. This represents a different vector v in your vector space. And this represents a third vector w in your vector space. And this represents some vector v, and then you're multiplying by some scalar, and then you get a different vector out of it. So you can easily verify that it satisfies all the properties required. So vector addition is commutative. So if you add like f of x plus g of x, that's the same thing as g of x plus f of x, because polynomial addition is commutative. And then there's also a zero polynomial, which if you add it to any polynomial, you get that polynomial itself. And then if you add up any three polynomials, you can either add up the first two, 7x squared plus 5x, and then add the third one, or you can add up the last two, 5x plus 13x squared plus 5x, and then add the first one afterwards, and then you get the same answer. And that's just saying that polynomial addition is associative. And then you take 7x squared plus 5x, and then there's an opposite vector, negative 7x squared minus 5x, so that if you add them together, you get 0x squared plus 0x plus 0, which was your identity from up here. And so all that's saying is that, like, you have different vectors, which in this case your vectors are polynomials again. So you can add them together, it commutes. There's an identity one, which if you add to anything, it becomes itself. You can add three of them up in any order you want, that's just associativity. And then each one has an inverse, which gives you back the identity. So these are all the statements which have to do with vector addition. And there are also statements that have to do with scalar multiplying. So you have your zero scalar, and if you multiply that by any vector or any polynomial, then you get 0x squared plus 0x plus 0, right? Because it cancels out everything. And so I put a little parentheses equals 0 in both of these lines, because most books, they just use 0 to represent the number and the vector, which is a bit weird at first, but you get used to it. And then you have your scalar 1 times any vector is just the vector itself. So that's just saying that if you multiply 1 times any vector, you get the vector back. And then if you multiply your vector 7x squared times the sum of two scalars, so 3 plus 5, then you can distribute the 7x squared to both of these, and then you get 3 times your vector plus 5 times your vector. And conversely, if you multiply a scalar times the sum of two different vectors, then you can distribute it on the right by saying this is 3 times your first vector plus 3 times your second vector. And the last property is that if you multiply two scalars together and then you scale this vector up by that, then you can just do it so that you multiply the vector first by the right scalar, and then you multiply this 5 times 7x squared plus 2x, which is a different vector, times your scalar 3. So I put all the properties as close as I could, aligning them with the properties on the left. So if you want, you can pause the video for a bit here and verify that these all match everything on the left. Okay, so you may have noticed in the last example that quadratic polynomials are essentially the same as the Euclidean vector space. So what I mean by that is you have polynomials of the form ax squared plus bx plus c, and on this side you have vectors of the form ai plus bj plus ck. So when you add up two vectors together, you essentially just add the coefficients, and you do the same thing when you add up vectors together. And here, if you scale up polynomials by a certain amount, you just multiply each coefficient by that real number, and you do the same thing for vectors. So for vectors, you have a very natural three-dimensional description of it, which is you have a vector ai plus bj plus ck, and that has an a component in the x direction, a b component in the y direction, and a c component in the z direction. So similarly, you can think about this abstract vector space of quadratic polynomials as being a three-dimensional vector space with your basis vectors as x squared, x, and 1. And so your ax squared plus bx plus c, it has an a component in the x squared direction, a b component in the x direction, and a c component in the constant direction. So these two vector spaces are essentially the same thing when you look at it from that perspective. And there's a theorem that formalizes this, which says that if you have two vector spaces of the same dimension, you can treat them in exactly the same way in terms of just adding the vectors together and scaling them up or down. And so what that means is essentially that they have an isomorphism between them in more fancy terms. So what is the dimension of a vector space? It's essentially like how many coefficients you can change independently. So here you can change it so that it has a different amount in the x direction, a different amount in the y direction, or a different amount in the z direction. And here you can change the coefficients of x squared, x, and the constant. So you can see that both of these are three-dimensional vector spaces. So you may ask, like, why stop here at quadratic polynomials? You can like increase to cubic and quartic polynomials and increase the dimension. So here I have an example of a quartic polynomial, which is just something times x to the fourth all the way down to your constant. And here you see that you have 5 different coefficients. So this is exactly the same as a 5-dimensional vector space. So if you could visualize 5-dimensional vector spaces, you would see that the picture is exactly the same as your Euclidean 5-dimensional vector space. Now, obviously you can't do that. If you can, please tell me how. I really want to know. But you can like not even stop at quartic polynomials. You can keep on going and say, okay, let's just increase this to a finite fixed maximum n degree polynomial. So if you add up two n degree polynomials, then you're still going to get an n degree polynomial, or at max an n degree polynomial. And if you scale an n degree polynomial up by some constant, you're still going to get an n degree polynomial. And your n degree polynomial has a 0 vector, which you can add to any of these polynomials to get the vector itself. And those are pretty much all the conditions that you need for a vector space. And so here, because you have n plus 1 coefficients that you can freely change, this is the same thing as an n-dimensional Euclidean vector space, if you could imagine things up that high. So you may ask, like, why stop at like finite dimensions? You can just do any polynomials, right? So if you add up two polynomials together, you get a polynomial. If you scale up a polynomial by a certain amount, you still get a polynomial. If you add 0 to a polynomial, you get that polynomial back. And those are essentially all the conditions that you need for a vector space, plus, you know, the properties that we saw earlier. And so that satisfies for any degree polynomial. But the condition is that after a while, all the coefficients need to go off to 0. And the reason for that is because polynomials just kind of become bad if you have like infinitely many things there, right? Because like 1 plus x squared and so on, that's just like 1 over 1 minus x, which is sort of like different from a polynomial now. So usually the way that you define this is you can say that the polynomials can be of arbitrarily high degree, but they must have finite degree. Or almost all the coefficients must be 0 is another way that's often said. So for example, you can have a linear polynomial, x plus 7. You can have a degree 10 polynomial, x to the 10th plus 9, x to the 7th plus 4x. Or you can just keep on going higher and just have something massive like this. And they're all still polynomials, so they're also part of this really large vector space. And so this is the first example of, you know, an infinite dimensional vector space. And since these polynomials here sort of represent an n plus 1 dimensional Euclidean vector space, this over here, sort of like, since you have an infinite amount of coefficients that you can change, you know, after a while they have to go to 0, but you can still choose them to be non-zero up to a point, and that point can be arbitrarily far away. So this sort of represents like an infinite dimensional Euclidean vector space. And things get weird around there, but we won't really be working with this, but we will be working with different infinite dimensional vector spaces. So yeah. Okay, so now we're on to our last couple examples of vector spaces, which are much closer to what we'll be working with later, but very different from the Euclidean vector spaces that we started with. And so the first one is just any arbitrary function over an interval. So what's a function over an interval? It's just anything where if you give it a real number between a and b, it'll spit out another real number. So you can have exponential type functions, you can have Gaussian type functions, or you can have a weird discontinuous steppy like function. And so these functions form a vector space because, for example, you can add up two different functions over an interval. Sine of x plus e to the x is still a function that's defined over this interval. You can add up the 0 vector, which is the 0 function, to any function. So e to the x plus 0, where 0 is just a function, is going to give you back e to the x. So 0 acts as the identity. You have negative functions, e to the x plus negative e to the x is 0. And then you can scale up functions. So e to the x times 5. We'll just scale it up by 5 and you get the function 5 e to the x, which is still a function over this interval. So these functions can get kind of wild. So for example, you can have this g of x function here, which is 1 if x is a rational number, and 0 if x is not a rational number. So this one is really weird because between any two rational numbers, there's an irrational number. But between any two irrational numbers, there's a rational number. Nevertheless, this is still a valid function because you can still plug in any value between a and b, and it'll just tell you whether that number is rational or not. So in our earlier examples, the Euclidean vector space, right, we had our basis vectors I, j, and k, and you would just add up the two components of vectors if you were to add up two vectors together. And similarly for polynomials, we had our basis vectors 1, x, x squared, and so on, and you would just add up the components of that. And even for our arbitrarily long polynomials, you would still have your basis vectors, you just had infinitely many of them. So this one is a bit stranger because the only real basis vector you can choose is something that's 1 on a certain point over the interval and 0 everywhere else. And the reason for that is like you can have something that's defined as e to the x everywhere between a and b, except for like at square root of 2, where it's defined as 0. So the only real basis you can choose is the indicator functions for values. So for any value k in the interval a, b, you define f sub k of x as being 1 if x is equal to k and is equal to 0 otherwise. And so you can reconstruct any function over the interval as a sum of these basis functions. So for some examples, you have your function g of x here. So you can define that as the sum of all k in the rational numbers of the indicator function f sub k of x. And so for example, if you plug in x is equal to 5/3, right, you can have something like f sub 2 of 5/3. That's going to be 0 because 2 is not equal to 5/3, or f sub 3 of 5/3, again 0. The only time that this is going to be non-zero is when you have k is equal to 5/3, right? Because f sub 5/3 of 5/3 is going to be equal to 1. And so if you have an irrational number x, like x is equal to the square root of 2, since you only have the indicator functions which are rational numbers here, you won't have the contribution from square root of 2. So for example, like if you have 1 plus x cubed, right, there's no x squared term in that polynomial. And another function that you can decompose into these things is x squared. And you can decompose that, you take all k in the interval a comma b, and you construct the sum k squared times f sub k of x. So what does it mean for two functions to be equal? It's just like for every input, they have the same output, right? So for example, let's say that x is equal to 7. So here, you can have f sub 5 of 7, that's going to be equal to 0 because of that. F sub 3 of 7, 0. F sub pi of 7, that's still 0. But if you have f sub 7 of 7, this part is going to be 1. And then that's scaled up by some coefficient k squared. And so in this case, this is going to be 1 if and only if k is equal to 7. So that'll mean that here you'll have 7 squared. And so this whole infinite sum is going to break down into just 7 squared times f sub 7 of 7, which is 7 squared times 1, which is 49. So if you plug in x is equal to 7, you get back that this is equal to 7. So these two functions are really the same thing. And I just want to point out quickly that this is like x squared considered as a function over the interval, not x squared considered as like the polynomial vector space. Two different things. But these bases are a bit stranger than the earlier one, even for infinite polynomials. Because for infinite polynomials, you had a countable amount of basis vectors, right? You can count them, 1, x, x squared, and so on. But the interval a comma b is uncountable. You can't take every single number and list them out between a and b. And if you haven't seen countable and uncountable numbers before, I recommend checking out something like Cantor's argument online. But the next example I want to mention is continuous functions over an interval, right? So for example, you can have square root functions, trigonometric functions, and stuff like that. And so these are like better defined. So for example, g of x here, that's not a continuous function. But the question is obviously what is a basis for these continuous functions? Now you could choose this as a basis, right? You can just say, okay, for every value here, you're gonna look at what the input is, take the indicator function, scale it up by that amount, and then put them all together. But that's the same thing as saying like, okay, what's the basis for the two-dimensional plane? And then you answer, well, there's I, j, and the k vectors. So that forms the two-dimensional plane if k is always 0. So that's kind of a dumb way of putting it because the two-dimensionality sort of restricts the coefficients of your basis vectors. So similarly, the continuous functions restricts what your coefficients can be. So like, by the way, continuous functions are constructed over any small interval x minus delta, x plus delta, the function is almost constant pretty much. So what that means is, like, say you have a sum of this form, and say you have like f sub 2 of x is approximately 5, the coefficient here. That means that if you have 2.001, then the coefficient here can't be very different from 5. It'll have to be approximately equal to 5. And f sub 1.99, the coefficient will also have to be approximately equal to 5. So that puts a bit more restriction on what the basis can be. And what a basis is, it's really the minimum amount of things that you have to add up in order to get all your functions. And here, if we have this as our basis, we're going to have some redundancy due to the nature of continuous functions. So it's really remarkable that there's a sweet spot in the middle here, which we're going to be dealing with, where you can express functions as the sum of trigonometric functions. So it'll be the sum of 1 cosine x, cosine 2x, cosine 3x, and sine x, sine 2x, sine 3x, and that's also a countable set. So it's amazing that even though there are an uncountable amount of inputs, and you might think that you need an uncountable number of things to express continuous functions, you actually only need a countable number of cosine series to be able to do this, and that's what we'll be getting to later. So the main takeaways of vector spaces is that a vector space is just something where you can add up two things and you get another vector. You have an identity vector where you add up anything to 0 and you get back itself. You have negative vectors, so a vector plus its negative is 0, and you can scale vectors by a real number and you still get a vector back. And so again, these functions over an interval will be what we'll be dealing with most in the future. So I'll see you next time, where we'll talk more about metric spaces and inner products.